Good day everyone. Today, this video, I'm going to discuss to you about a problem involving from the chapter 4 response to first order systems. Chapter 4 from the book Process Systems Analysis and Control. The author is Cogonor and LeBlanc from the 3rd edition. So let's have a simple problem for this topic. 4.8. The mercury thermometer of problem 4.6, which is in the book, is again allowed to come to equilibrium in the room air at 75 degrees Fahrenheit. Then it is placed in the 400 degrees Fahrenheit oil bath for a length of time less than 1 second and quickly removed from the bath for a length of time less than 1 second and quickly removed from the bath and exposed to the 75 degrees Fahrenheit ambient conditions. It may be estimated that the heat transfer coefficient to the thermometer in the air is 1/5 that in the oil bath. If 10 seconds after the thermometer is removed from the bath, it reads 98 degrees Fahrenheit. Estimate the length of time that the thermometer was in the bath. So let's try to solve this problem. So we have a review. So from the book, we all know that y of s over x of s equals to 1 over tau s plus 1. If you don't understand this, so you must review into chapter 4, which is the response of first order systems, which is equal to the ratio output over input. So the problem, if a step change of magnitude a is introduced into a first order system, so the x of s would be equals to a over s. Now substituting this x of s into this function y over s over x over s equals to 1 over tau s plus 1, so we have y over s equals to as times the 1 over tau s plus 1. Now, as you can see in this expression, we can solve this by partial fraction. So again, you have to review about the partial fraction to solve this problem. So I'm not going to discuss about partial fraction anymore, as I am to test you about how to solve this problem by using partial fraction. So the result would be y over s equals to as minus a over s plus 1 over tau. Now we're going to solve this using the Laplace transform. So you're going to review again about the Laplace transform and its inverse Laplace transform. So the answer would be y over t equals to a over s to a minus a e to the negative t over tau. So we have the final answer, the y over t equals to a times 1 minus e to the negative t over tau. So after getting the expression, we have from the problem 4.6, we have Ts equals to 75 degrees Fahrenheit. S means that it is in a steady state condition. So we have the time constant of oil, which is equals to 10 seconds, or the tau oil equals to 10 seconds. So from the problem, it states that it may be estimated that the heat transfer coefficient to the thermometer in air is 1/5 that in the oil bath. So let's have the equation. The time constant, or tau which is tau oil, equals to mc over h oil over a. of MC over H oil A. And also for the tau air, which is equals to MC H air over A, H air A. So combining these two equations, we will have tau air over tau oil equals to H A, which is the heat transfer coefficient of oil over heat transfer coefficient of air, which is equals to 5. So getting the heat constant for air, which is times 5 of the heat constant of oil, which is 5 times 10 seconds would be 50 seconds. So we have now the time constant of air, which is 50 seconds. Then from the equation earlier, we have that y of t equals to a 1 minus e to the negative t over 10. So let's just change that y into t, so it would be more easier. So t of t equals to a times 1 minus e to the negative t over 10, which is this 10 means that we are now focusing for the oil bath. And this a, as I've discussed earlier, is the steep change of magnitude. And from the step change of magnitude, we have that from 400 minus 75, which is room air temperature 75, and then place in 400 degrees Fahrenheit. So the change of magnitude would be the T of T equals to T1. Let's say T1 equals to 325 from 400 minus 75. This is the A, 325 times 1 minus e to the negative t over 10. So this is, again, let's focus on for the oil bath. And now we have that T max equals to 75 plus T1. So what I've said earlier is, from the equation here, we have that for the oil bath. And now we have the T max. From the T max, it is the temperature at maximum of step function where the oil bath will end and there will be the start for the air. So we can have that the T max would be the T1, which is T1 from the oil bath, added by the 75. So this would be the T max temperature from the middle of oil bath and the start of air. The end of oil bath and start of air. 75 plus 355 times 1 minus e to the negative t over 10. Then now we have the equation from the air, which is T of S equals to 1 over S times 75 minus T max over tau air S plus 1. So let's remind you earlier that last equation would be from that oil bath, and now let's focus now on the air. So we have still the same from what I've solved earlier. So let's just skip from that part and let's go to the answer. The answer would be the Laplace transform for this would be T of t equals to 75 minus T max times 1 minus e to the negative T2 minus T1 over 50. And T2 from the problem itself, that T1 plus 10 seconds. Now let's solve this by using again the equation earlier, that we have that from T of t equals to 75 minus T max, and having the expression added by T max to get the T max. So T max plus from the earlier expression Tt equals to 75 minus T max 1 minus e to negative T2 minus T1 over 50, which is T2 minus T1 equals to 10 seconds. So we have 98 equals to T max plus the expression 75 minus T max 1 minus e to the negative 10 over 50. So solving for T max, you can solve this by using your scientific calculator. So we have T max equals to 103.09 degrees Fahrenheit. And now we can now solve for the T1 by, let's go back to the previous previous equation, the T max equals to 75 plus 325 1 minus e to the negative T1 over 10. So substituting T max, which is 103.09 degrees Fahrenheit, which is equals to 75 plus 325 1 minus e to the negative T1 over 10, and substitute and getting the expression T1 by using your scientific calculators. So we have the T1 equals to 0.904 seconds, which is the time that the thermometer was in the bath. So this is our final answer. T1 equals to 0.904 seconds. So to make the problem more easy to imagine, so let's have a graph for this. So we have our oil bath, which is 400 degrees. We have from 400 degrees Fahrenheit, and we have our T max, and we have from 75 degrees to 98 degrees. Now let's see so assuming that this would be the graph for our problem, for our equation there, and we see that this line would be the boundary for the oil bath and for the air temperature. Now we have that this is the T1, so this area, and this is this will be at our T max, which from what I said earlier, the maximum of step function where the oil bath will end, and the air temperature will start, or the air will start of air. Now, and also we have that from the time constant of 10 seconds to 50 seconds. So we have that in this area, that we have that for T1 at 0.904 seconds. This will be the result. This would be the area for the 0.904 seconds. So I hope this video will help you more about understanding about the problem about the step function for the response of first order systems. And I hope this video is helpful for you.